Welcome to this explainer. Today, we're diving headfirst into the Cambridge IGCSE 0625 syllabus, and we're going to unpack the entire thermal physics section. Look, if you've been staring at your textbook, just trying to piece this all together, don't sweat it. We're going to break down the core concepts, the math, and the best revision strategies using the source material to make it all totally accessible.
Okay, let's dive into this. Before we look at a single formula today, I really want you to look at the world around you. Have you ever wondered why railway tracks are built with those small gaps between the steel rails? Or think about a glass jar with a metal lid that's just stuck tight. Why does running it under hot water magically loosen it up? Well, the answer is thermal expansion. When matter gets hot, its particles gain kinetic energy. They start moving faster, and they literally push further apart. So you see, this abstract physics stuff, it's actually everywhere around us, just quietly governing the physical universe.
To master this, here's our roadmap for today. 1. Cracking the 0625 syllabus. 2. Matter, motion, and heat. 3. The math of temperature. 4. Boiling versus evaporation. 5. How heat actually moves. And finally, 6. Winning your physics revision. All right, let's jump in.
Section 1. Cracking the 0625 syllabus. When you're preparing for any major exam, knowing the exact layout of the battlefield is literally half the battle won. So here's the exact breakdown for the extended tier assessment, pulling data directly from Tutopia. You've got 3 external papers to tackle. Paper 2 tests your quick recall and fundamentals, that's 40 multiple choice questions in 45 minutes. Then comes Paper 4. This is the heavy lifter. We're talking 80 marks of structured theory questions that'll take an hour and 15 minutes. And finally, Paper 6 is your alternative to practical, which tests your experimental skills for 40 marks over an hour. You absolutely need a specific strategy for each paper style if you want to snag that A star.
Now, the IGCSE syllabus broadly covers 6 topics, but today we are laser-focusing our attention on mastering the second one, thermal physics. It's a pretty dense, heavy-hitting section for sure, because it connects everything from the microscopic movement of individual atoms all the way up to global weather patterns.
Section 2. Matter, motion, and heat.
To really understand thermal physics, we kind of have to shrink ourselves down and move into the invisible world to see how particles actually behave. This comparison perfectly illustrates the extremes of the kinetic theory of matter. In solids, you've got these very strong intermolecular forces. Think of the particles as being locked into a rigid, regular grid, right? They're only able to vibrate in fixed positions. That's exactly why solids hold their shape and can't just be compressed easily. But gases, completely different story. They have practically zero intermolecular forces. They are basically the Wild West of particles, just flying around randomly at incredibly high speeds. And because there is so much empty space between those flying particles, gases are highly compressible.
But wait, how do we actually know these particles are constantly moving if we literally can't see them? Enter Brownian motion. Back in 1827, this Scottish scientist named Robert Brown observed something super fascinating under his microscope. He saw tiny pollen grains suspended in water, and later, smoke particles suspended in the air, just dancing around in these random, unpredictable zigzag patterns. The smoke wasn't moving on its own, it was being constantly bombarded from all sides by invisible, incredibly fast-moving air molecules. This simple, elegant observation provided the very first direct visual evidence proving the kinetic theory of matter.
So if heating something up adds kinetic energy and makes its particles move faster, what on earth happens when you cool it down? As the temperature drops, particles lose kinetic energy and they start to slow down. But here's the catch. They can't slow down forever. At exactly minus 273.15 degrees Celsius, we hit a hard absolute limit. This is absolute zero, or 0 Kelvin. At this precise freezing point, particles have absolutely zero kinetic energy, meaning it is physically impossible to get any colder than this. No way around it?
Section 3. The math of temperature. Smoothly transitioning from concepts to formulas, now let's look at the official CIE IGCSE formula sheet. Now, what's really interesting about this slide is how beautifully it consolidates what you actually need to know. If you focus your eyes on the Chapter 2 thermal physics section, you'll see we're dealing with very few core equations, but man, they carry massive weight on the exam. The 2 big ones are the energy equation relating to specific heat capacity and Boyle's law for gases. Let's break those down.
Specific heat capacity is a huge favorite for examiners. The equation is Q equals m times C times delta T. Honestly, it simply measures how stubborn a material is when you try to heat it up.
To ground this definition, just try to picture that classic lab experiment. You take a metal block, wrap it in an insulated material to stop the heat from just escaping into the room, and you insert an electric heater and a thermometer. By measuring the electrical power going into the heater and tracking the temperature change over time, you can calculate the exact specific heat capacity of that specific metal.
Next up, we have Boyle's law for gases, which is written out as P1V1 equals P2V2. I love this law because it's just beautifully logical. Imagine you're holding a sealed syringe full of gas. If you keep the temperature totally constant, but you compress the plunger, you are shrinking the container's volume. Now, you haven't changed the number of gas molecules inside, right? But now they're trapped in a much smaller space. So what happens? They are forced to collide with the walls of the syringe much more frequently. More collisions equal more force per unit area, which means a huge spike in pressure. Boom. Pressure and volume are inversely proportional.
Section 4. Boiling versus evaporation. Okay, pay attention to this next one, because this distinction constantly trips students up on exams. While boiling and evaporation both turn liquids into gases, they are completely different mechanisms. So, the crucial point is understanding that boiling requires a specific temperature. The boiling point, obviously. And it happens entirely throughout the bulk of the liquid, which is exactly why you see bubbles forming everywhere inside a boiling pot. But evaporation, that happens at any temperature and exclusively at the liquid's surface. Only the most energetic molecules right at the surface have enough speed to break those intermolecular forces and escape into the air. And because those high-energy molecules take off, they leave the lower-energy molecules behind. This perfectly explains why evaporation always causes a cooling effect.
Section 5. How heat actually moves.
The universe absolutely hates imbalance. Heat will always transfer from hot to cold until it reaches thermal equilibrium. And one of the most dynamic ways this happens in fluids is through convection. A perfect, real-world illustration of this is the daytime sea breeze you feel when you're hanging out at the beach. Let's walk through it. Step 1, the sun's radiation hits both the land and the ocean, but the land heats up way faster. Step 2, the air right above that hot land gets heated by conduction, it expands, it becomes less dense, and naturally rises straight up into the atmosphere. Step 3, this rising air creates a low-pressure zone over the land, so the cooler, much denser air from out over the ocean rushes in to fill that gap. That rushing air hitting your face, that is a massive, continuous convection current in action.
And then, of course, we have radiation, the transfer of thermal energy via electromagnetic waves. What's crazy about radiation is it doesn't even need particles. It can travel right through the literal vacuum of space. I really want to call out this golden rule from our sources here. Matte, dull, black surfaces are both fantastic absorbers and fantastic emitters of infrared heat. In stark contrast, shiny, silver, or white surfaces, they're terrible absorbers, but they are incredible reflectors. This is exactly why the inside of a vacuum flask is shiny silver. It bounces the heat of your coffee right back in to stop it from cooling down.
Section 6. Winning your physics revision.
Okay, so you've got the concepts down, but how do you actually turn all this theory into an A star on exam day? Please remember this. Just passively reading your textbook cover to cover is not actual revision. It's just reading. The highly actionable flow recommended by Tutopia goes like this. First, start with focused notes and videos just to grasp the concept. Next, you must drill topic-specific practice questions. And here's a massive pro tip. Try explaining your method out loud to an empty room. If you can speak it and explain it, you actually understand it. Third, don't just check if you got the right answer. Read the worked solutions. You'll often discover way faster, more efficient methods. Finally, in the last 4 weeks before the exam, you need to shift entirely to full pass papers, strictly under timed conditions, to master your pacing.
As we wrap up this masterclass, I really want to leave you with a pretty provocative thought based on what we explored today. What would actually happen to the physical universe if every single atom lost its kinetic energy and just stopped moving completely? Think about it. At absolute zero, everything halts. The implications for matter, for planets, for the fabric of space itself are absolutely mind-bending. Keep marveling at these crazy extremes of physics, apply the revision methods we talked about, and you'll be perfectly primed for our space physics explainer coming up next. Happy studying, everyone!